Swayam Prabha. Digital India. Educated India.
Welcome back. Let's continue the discussion on the turbulence, and so we are pretty much looked at all the characteristics, scaling and everything. Now the last part we will look at the frozen turbulence, and then we move to the modeling aspect of it. So this is what we looked at in the frozen turbulence. There is a AD of size this, where this is our measurement locations, and if the turbulence or turbulence intensity, which is, so this is what happens, which is scales like u square by L minus u bar u by L, like u bar minus 1. So that means AD quickly advected by the mean flow such that it does not have time to change. So the implication is that measure time series it is in fact a space series. So the transformation time to space, where 1 by u square del 2 rho 1 by del S2 goes to del 2 rho 1 1 by del R2, and omega by u bar tends to, so essentially the time transformation into space. Now if you look at that energy spectra of that thing, so this is a relation thermodynamic energy and 1D energy spectra. So this is our u prime square. Then if you look at the energy containing range, so the length scale would be order of L, velocity scale is of that. So the energy containing range, it will be u square L this. In the dissipation range, length scale and the velocity scale, so the energy would be like this. And inertial range, which is in between L and L naught, they will the length scale and the, so this is what you get in the inertial subrange. This is an Kolmogov's minus 5 by 3 spectra. So this is very well known that in different, and if you put that thing in a spectra, this is your normalized spectra with the wave number space, and that is the different. This is our energy containing range, this is inertial range which follows this, and this is dissipation range. So each range the energy spectra is different. So the requirement is that Reynolds number is sufficiently large and spectra separation between micro and macro structure. So now we can pretty much look at this relation between 1D energy spectrum and 2-point autocovariance for a statistically homogeneous turbulence. So this is shift the 2 integral into 1 and the limit, so that u bar prime will look like this. Now if you change the integration sequence over this, you do this algebra, finally you get back this. And if we R11 tends to 0 in for R range between these, so this will become an scale like that. Okay. So that is what you get. So that pretty much gives you an idea about scales, spectra, how to calculate that, and some of the basic example of homogeneous turbulence, statistically homogeneous turbulence, we have looked at it. Now with that information, we can move to the modeling aspect and look at what are the critical features that one has to take care while talking about the modeling part. Just to recap about the properties, so this is again which we started off. So the flow feature is truly unsteady and 3-dimensional, so that means it is essentially chaotic. So there would be different kind of vertical structure, there could be large scale structure, small scale structure. then it is high enough Reynolds number flow. This is dissipative in nature and it allows effective in mixing. Now, that is how we look at the Reynolds number, which is a non-dimensional number, to look at it whether the flow is really turbulent or not. Now, what is the role of this numerical modeling? So, it essentially require an understanding of turbulence and the ability to predict the turbulence for any given application. So, for example, one can think about that we can increase the turbulence in chemical mixing or heat transfer when fluids are dissimilar properties. Also, turbulence increases the drag due to increased frictional forces. So, I mean, historically only measurements was possible for limited configuration, but now with the advancement of the computational fluid dynamics tool or the numerical tool, now the real life complicated problem can be looked at in details. So one can think about the numerical modeling of turbulence can serve to improve the engineer's ability to analyze turbulent flow in design, particularly when the precise measurement cannot be done, or rather the measurement can be precise and also expensive. So, one has to make a choice. So, the ideal turbulence model should introduce minimum complexity while capturing the essential flow physics. So, the ideal turbulence model, that should be with minimum complexity while capturing the relevant physics. So, you have a turbulence model and near wall treatment if it is a wall bounded flow. So, and then you have a computational grid. So, these are the turnaround time is a constant. Computational resources are also an issue for turbulence model and computational grid, because what kind of turbulence model one will use. So, what are the resources available, then what is the expected time for calculations and all this, but turbulence model or near wall treatment are actually dictated by the flow physics or the accuracy required. So, this side will actually push you that what model one should use, but then at the same time you have a problem dimension and also the required time estimate and the resources available, which has to be taken into consideration, and that is why one has to make a choice. Now, this can be modeled in multiple ways with different degrees of complexity. So, the simpler one can use the correlation based calculations, which are often used to be used earlier days, like Moody's chart, Nusselt number correlation, and once you use those correlation and you get the design point data to use that. So, that right now I would say this is a sort of an history, because nobody do that, because the kind of computer or computational facility available these days, one can easily do some simulations. Now, then next is that, so this is the increasing order of complexity, either integral equations like derive some ordinary differential equations, and this is also not used very often. Now, the third option, which is the Rand's equation, this is quite widely used, not only in the academic perspective, also in the industrial perspective, because the calculation time is quite small and you can get reasonable accurate results for a large scale applications, and that is where people can consider this one or use it for the design calculations. And then LES is another choice from RANS to LES, which will increase the complexity, but also it captures the turbulence in a better way compared to RANS. And finally, if possible, like if you have enough resources, I mean in terms of computational power, then you can go for DNS for real life problem, and that is how this is the increasing level of complexity. Now, what model does what? So, this is my, if you look at the energy spectra quickly, this is my large scale energy containing structure, then energy cascade takes place. This is the energy cascade, and then finally it comes to small scale where it dissipates. So, this is my length scale at large scale, then this is my smallest scale at the dissipation range. Now, when somebody use DNS, it resolves all the scales starting from the large scale to small scale. So, that is why it is so expensive computationally, because one, and you can see these scales, and already we have seen that they are somehow involve the Reynolds number, and then when you go for the large scale real life problems, the Reynolds number is quite large. Now, in between LES, it resolves most of the energy, the large scale energy and the intermediate energy, only model a small portion of the small scale, with the assumption that these scales are universal in nature. And RANS, pretty much the complete spectrum is modeled. So, you do not assume or consider the energy cascading effect, rather you assume everything is sort of an isotropic situation and mean. Now, approach one can think about. So, this side you think about the increasing the cost, in the sense computational cost. This at the same times it increases the physics. So, that means more and more physics you want to resolve or you want to capture, your computational cost will go up, and that is where one can start off. This is a zero equation model, that is mixing length kind of model, where you have an algebraic equation, but that has lot of disadvantages for wide range of flows. Then one can do one equation model where they solve for the eddy viscosity using a transport equation, and this is quite applicable or handy, I would say, applicable for external aerodynamic problem. Now, then the second layer of complications which one can take care is the series of two equations model, like standard K-epsilon model, RNG K-epsilon, SST K omega. There are a series of two equations model which could be used, and then we can look at the Reynolds stress model, which will use second order closure, and where the stress individual transport equation for the Reynolds stresses are solved in this RSM model. Then after RANS, one can include more physics, resolve more scale, so one can go for LES. And then if you want to increase more complexity, more physics into it, then one has to go for DNS. Now, what are the issues with DNS? So, currently DNS is the most exact approach for modeling turbulence, because no averaging or no approximation is made. So, the smallest scales are solved due to resolution. So, at the up to the Kolmogorov scale it is resolved. So, the DNS simulations scales with Re to the power L u prime L by eta, where REL is order of 1% of Re. So, if you take an example of a simple flow persistent cylinder, this will take some 8 million cells like that. but as I said, given a current processing time and memory, it is still possible. So, there are some advantages, there are some disadvantages. Advantages, it can be used as numerical flow visualization and can provide more information compared to experimentation, and it can be used to understand the turbulence or mechanism of turbulence production and dissipation. The disadvantage, primarily computationally expensive, and it is still limited to small geometries. Now, second approach is the LES, which is in between DNS. So, this is also 3-dimensional, equally it is not like DNS, but it is also computationally very expensive, especially wall bounded flows. So, in LES it solves for large scale motions and models the small scale motions, and the premise of LES is that the large scale motions contain the most of the energy. So, and the small scales are more universal in nature. So, that is why. Now, the LES equations are obtained by filtering operation, and the filter produces the equations where you get, like, if you say this is my filtered equation plus del del xj rho ui uj plus del del x mu of del ui del xj plus del u bar by del xi, and also tau ij. So, the tau ij is your subgrid stress term, which is model. So, different subgrid scale models are available. Now, if you go to RANS, so RANS has quite a bit of advantage over DNS and LES. So, this is less expensive. Typical engineering flows can be quickly solved, quick solution can be obtained, but this approach would be more turbulence by averaging the understanding of turbulence. So, averaging process has some problem because it creates terms that cannot be solved analytically, but this is quite widely used for design purposes. Okay. Now, one can think about how we do the, and this is already we have discussed in details. In RANS, you take the ensemble average, this is your velocity signal, and then this is ensemble average signal, this is how the ensemble average is. So, you take number of samples and ensemble average becomes, and your decomposition is the instantaneous flow field is the mean plus the fluctuating component, and if n is small, then there could be error, which is the statistical error. If n is large, then this can be minimized. So, if you put these things together, so any variable in RANS, there is a 2 component, means plus fluctuating component, and this phi could be anything, and then when you look at the Navier-Stokes momentum component, this is what you get back, this is your Reynolds stress term, and there are closure which involved in modeling the Reynolds stress term, and that gives rise to the different kind of model that we have already discussed, like RANS based model. And once you substitute this mean and fluctuating velocities in the instantaneous Navier-Stokes equation, so this is what you get the RANS equation, and these Reynolds stress terms are modeled, and that will give you different equations. So, the closure models are essentially that one can have 0 equation, which is basically mixing lane model, no transport equation, then 1 equation which is transport equation for the either kinetic energy or the eddy viscosity, two equation models which is have all sort of K epsilon model, RNG K epsilon, K omega model. So, all two equation based model and the second order closure like RSM based model. So, this is how you go with the increasing complexity, where you solve the individual stress component and it does not use any Boussinesq hypothesis. So, many turbulence models are based on this Boussinesq hypothesis, and it is observed that it decays unless there is a shear in isothermal incompressible flow. So, it is found that turbulence actually increase the mean rate of deformation, and the viscous stresses were given by del u by del xj, where del uj by del xi, and the Reynolds stresses which are modeled as the eddy viscosity time del ui by del xj, this is mean del uj by del xi. So, this is the mean component or mean standard strain, where mu t is the eddy viscosity. So, this mu t is the turbulent viscosity or eddy viscosity term. Okay. So, this can be correlated with your density and the kinematic viscosity. This is essentially not homogeneous in nature, it actually varies in space. However, if you assume to be isotropic, it is the same in all the direction. So, that is quite often used for some of the application. Then you have turbulent Smith number for scalar property or any scalar field. So, we have a unclosed term for the scalar flux. So, this is what we close the scalar term, stress term, through the gradient hypothesis. This is called gradient hypothesis, and this gamma t is your turbulent diffusivity. Okay. Now, the turbulence diffusivity, this is calculated from the turbulence viscosity using a model constant which is known as turbulent Smith number, like sigma t is mu t by gamma t. So, the Smith number varies for 0.7 to 1. So, that remains pretty constant for large scale problem. Then once you go to mixing length model, where mixing length model, this already we have seen nu t is essentially velocity scale into length scale, where velocity scale varies that del u by del y. So, this is proportional to the gradient of the velocity. So, finally, the nu t equals to Lm square by del u by del y. So, this is what Prandtl proposed in 1925, Prandtl's mixing length model, and this mixing length constant which one has to provide in his calculation a priori. That is why the biggest disadvantage of this particular model, though it is simple, that this mixing length definition is not known a priori. So, the advantage, there are certain advantages like easy to implement, fast calculation time. So, it can provide you reasonably good prediction for simple flows. Disadvantage, as I said, that it is not capable of solving the large, the problem for a wide range of Reynolds number, and that mixing length has to be provided a priori, which is a problem, but it is used sometimes for simple external flows also. But these days it is seldom used because there are advanced models which are available. So, that is why now this is one equation model, where it is a single conservation equation for turbulent viscosity. So, that contains there would be a equation which is have a right hand side term. So, this is quite often used in external aerodynamics calculation. This is economical and quite accurate for attached wall bounded flows with mild separation and recirculation, but this is quite weak for massively separated flow, free shear flows and decaying turbulence. So, this has quite a bit of limitations, and that is why it is not often used extensively. Now, then one can move to the two equation model, where the again using the Boussinesq hypothesis, the Reynolds stress term can be approximated like this, where the turbulence viscosity is approximated using some model constant and in the presence of kinetic energy and the dissipation. So, this is what we have already looked at it, and the turbulent kinetic energy is estimated like that, and the dissipation rate of the turbulence. So, this is used in two equation turbulence model. Now, if you look at the standard K epsilon model, which we have already looked, this is the convection term, this is production term and diffusion term and the dissipation term. This is in a steady situation, and the dissipation rate, which is the solution for epsilon, this is the convection, generation, diffusion, and these are the model constant. So, as I said, this is written for steady, incompressible with no body forces. So, that is your two equation model. Now, the K epsilon model, it focuses on the mechanism that affect the per unit mass. So, this is how you get the kinetic energy, and finally, nu t is estimated like k square by epsilon. Now, the mean flow kinetic energy equation, which is rho k by dt plus delta dot rho k u del dot minus p u plus 2 mu u e I j minus rho u u I prime u j prime minus 2 mu e I j minus rho u I prime u j prime dot e I j. So, here this is the first term, second term, this is third, fourth, fifth, sixth, seventh. Here E I j is mean rate of deformation. Now, the first term is the rate of change of k, second term is the transport of k by convection term, and the third term is the transport of k by pressure, fourth term is the transport of k by viscous stresses, fifth term is the transport of k by Reynolds stresses, sixth term is the rate of dissipation of k, and seventh term is the turbulence production term. So, that is what you look at in the mean flow kinetic energy equation. We will stop here and continue this discussion in the next lecture.